Hello everyone, welcome to our CeADAR Tech Talk series. So just a bit of the logistics. So we are recording this video. So normally we have all questions at the end of the presentations, but this is an interactive session. So I guess like they may ask participants some questions during the workshop. So if you answer their question, that means you accept that we are going to record you in that. So for our tech talk today, we are going to have Brannigan, and Liam is going to give a talk on the Pandas library. I hand it over to Liam.
Hi, Con. So thanks for coming along this morning. The first thing is the workshop materials. So there's kind of two groups of attendees on this. There are people who are in CeADAR who may have got this from an internal email, but in the chat, I've just put a link, a tiny URL link to the material download. So that'll download it from, this link will download the materials from one of my S3 buckets. And then there's some fairly simple installation instructions. So the workshop materials are basically just a Jupyter Lab notebook and a CSV file. So if you can get the Jupyter Lab notebook running, and the CSV file will be in the same directory, then we'll install the other dependencies in the first line of the Jupyter Lab of the notebook. Okay, I'm going to share my screen now, so see if I've actually got permissions to share. Okay. Yeah. Okay, so you should be able to see the screen with the Jupyter notebook, is that correct?
Yes.
Okay, I'll just check. Okay, so I'm going to be kind of focusing on this. If either Quan or Maeve or someone, if you see that there's questions in the chat and I haven't spotted that, I'd appreciate it if you just kind of call that out to me. Okay, so here's what we're going to look at today. First of all, just try and get the notebook up and running. It'll take a couple minutes to kind of get started, but in practice, if it doesn't quite work here, we'll just be kind of following through the notebook, and so you can just kind of listen and follow on and get the notebook installed afterwards if you want to go back through it yourself. So the simple idea I have today is to work through a notebook where we do some forecasting of electricity demand and use polars to do that. So in this notebook, what we're going to talk about is sort of how we load data with polars, how we configure it for kind of making it nicer to work with in interactive mode, simple ideas for how we inspect the data frame, and then how we select rows and columns. So this is really an introduction to the polars API. Then I'm going to talk about some of the kind of bigger kind of ideas underneath the hood. So the first one is that we have fast track algorithms and sorted data. The second is that polars has a lazy mode with query optimization. And then we're going to talk about how we work with larger than memory data sets. I'm also going to touch on visualization and things like interacting with other tools in the kind of PyData ecosystem. And finally, we'll just build a simple machine learning forecasting pipeline. So just a quick introduction for myself, that my background is actually as a climate physicist, did my PhD in Oxford about 10 years ago. After being a postdoc, I joined Analytics Engines, which is a Belfast-based data consultancy, and then founded my own company called RowSignal. If you click on the RowSignal website, I write lots of blog posts about polars and about best practices and things you might not know about. So if you're interested, click on that and you'll find kind of dozens of blog posts I've written over the last year to kind of explain how to go at using polars. I have deployed kind of in production machine learning pipelines on this kind of idea with polars for a company called the Electric Storage Company. This is what I've been working on for the last 6 months. And they're a Belfast-based startup working in the renewable sector. So if you have a battery and solar panels and wind turbines, and you have to tell when should you charge the battery, when should you sell out energy to the grid, when should you do various other things. I've built the kind of machine learning element of that and then used polars in production. So that's been some really good experience. I've been a contributor to the polars library for the last year. Polars is written primarily in Rust, and I think I've contributed about 1 line of Rust code Instead, I focused on communication and accessibility. So I've written sections of the official user guide, and I've written lots of doc strings and examples that you'll find in the API. On the back of that, I created this data analysis with Polars course on Udemy. And so that's a kind of introductory course to get you kind of up and running with Polars very quickly. So for anyone from CeADAR, I've provided the course materials, and anyone else can access the material on Udemy. And on LinkedIn, I post a lot on LinkedIn, try to kind of find, as I come across new ideas and new things I think people will find helpful, I kind of post those on there and kind of keep people up to date with new YouTube videos or anything else I'm making. So that's a bit about me. If you have got the notebook up and running, then you can uncomment this cell and run it. And this will install the dependencies we have for this notebook, which are Polars, NumPy, CatBoost, Altair, and Vegafusion. Okay, so we'll crack on with some sorry, just checking the chat there. We'll crack on with some imports. I've imported these datetimes from the Python datetime module. And that's because Polars kind of leans on these heavily for filtering of datetime. So unlike Pandas, where you can do a lot of datetime work with strings, Polars wants actual datetime objects. And that's because you can end up having these silent bugs where you put it in one date format and Pandas thinks it's a different date format. And that Polars has got a lot of emphasis if you were to follow the developer chat in terms of avoiding silent bugs, making things explicit. And this is kind of one manifestation of it. We import Polars as PL, which is standard. And we'll also cover briefly this Polars get selectors submodule. This is a new idea that's been introduced. And the idea is that it makes it easy to work with multiple columns and be able to kind of identify what columns you want to work with. Going to import NumPy and CatBoost for the machine learning part. And for the visualization examples, I'm going to be using Altair and Vegafusion. So I really like Altair as a statistical plotting library. I will kind of discuss Matplotlib and Seaborn and Plotly. Well, I don't discuss them directly, but I'll link to a blog post where I've written about how Polars works with these below, and also about what this Vegafusion stuff is and how server-side rendering works with Altair in recent versions. So as I go through, I'm going to refer to other sources to kind of give you more information on things. A lot of them are from things in my course where I go into a lot of detail, but I'll also refer to some blog posts and things like that as we go through. Okay, just kind of a high level kind of thought about what Polars is at a glance. Firstly, it's a data frame library for tabular data. So 2D data, unlike say something like Xarray, which works with n-dimensional data, it's very much a kind of data frame library in the mode of Pandas, Dask, and Spark. There are APIs in Rust, Python, SQL, R, and Node. On the entire query engine really is written in Rust. And all these other languages, these are really thin wrappers that just call as quickly through to the Rust code as possible. So this is a difference with Pandas, where if you're ever debugging Pandas code, you know that often there's kind of like a number of layers of Python code before you get to the optimized C code underneath. Whereas if you were to go and look at a kind of standard Polars function in Python, you'd see that it kind of proceeds as quickly as possible to actually just doing everything in Rust. And the idea is that because Polars is built with the idea of having multiple APIs, that if you do as much as possible in Rust, then it makes it more easy to have these other language bindings. Polars has built-in parallelization. This is primarily a contrast with Pandas, where a lot of operations are still working in serial. And so to parallelize things, you often need to bring in kind of a wrapper library like Dask or Modin. Polars was built with parallelization built in from day one, which is one reason it's built in Rust, which has really good support for multi-threading and concurrency. So that means that whenever the algorithms are designed, they can be designed to kind of optimize where the parallel kind of operations happen, kind of on a full query basis. Whereas if you're using something like Dask, you've got kind of parallelization, which might be sitting in Dask, might be sitting in Pandas, might be sitting in NumPy, and so on. It scales to larger than memory data sets, not for every operation, but for many operations. And I'll talk a bit more about that below. And that kind of leads to, well, what are the use cases for Polars? So the most obvious ones are people who are using on a single machine, Pandas or Dask. But on the Polars Discord, one thing we commonly find is that people who are currently using Spark because their data is too big for Pandas, and then they jump to Spark, which comes with, it's a powerful library, but it comes with a lot of infrastructure overhead. whereas they find that because of the scaling to larger than memory data sets with polars, they can actually run their kind of query either on their current laptop or move to like just a single AWS instance with a bit more memory and run kind of big problems on that. And so that really simplifies their infrastructure, because for one thing, they don't have Pandas code and Spark code. And secondly, they'd just be able to run things on a single machine and not have to worry about distribution. Another contrast with the kind of Pandas ecosystem is that up until recently, Pandas was entirely built on NumPy as where it stores memory in the backend, whereas Polars is built on Apache Arrow. And Apache Arrow was really built to kind of, well, NumPy was really built originally as a kind of linear algebra kind of library, rather than specifically as a data store for tabular data. And so that meant there were issues with things like how it stores missing values and so on. Whereas Apache Arrow was really designed to kind of address all these issues and be really a standard data store for tabular data that would work across different languages and processes. One consequence of that, and generally the Polars developers' attitudes, is that Polars also has very strong type security. So kind of the Pandas issue where if you've got an integer column with missing values, that it will cast out to floats. That's the kind of thing that never happens in Polars, because it really takes type security seriously. And actually some people think it takes it too seriously, so it doesn't like you mixing 64 and 32-bit integers. And some of the recent discussion on developers has been, okay, are there ways of actually relaxing that a little bit if you want it? Okay, well, I think maybe it'd be most useful if when we come to the Q&A at the end to kind of discuss this and people's experience and relations with other libraries, once you kind of got a sense of what Polars can do as we go through. I'm going to start off thinking about with loading data, so with input-output really. And Polars supports these days a wide range of data sources, CSV, Parquet, Arrow, and also more kind of businessy things you might encounter like JSON, Excel, and reading and writing from databases. Most people, I think a lot of people now are using Parquet for anything above small data set sizes, but if you are still using CSV, if you're switching to Polars, it is a great time to use Parquet. With a Parquet file versus CSV will be much smaller on disk, maybe like 10 times smaller compared to your CSV file. It'll read 4 or 5 times faster. And it also really integrates well with Polars, because Polars can do clever things like spot that you only need certain columns of the data set actually in memory. And with Parquet, you can actually extract column by column like that in a way that you can't with CSV. So highly recommended if you haven't already to think about this as an opportunity to move from Parquet to CSV. First bit of code here, we're just going to read in the CSV. It's a small data set here, so I'm not going to bother with Parquet. And you see in many cases, the syntax is similar to Pandas. So instead of Pandas read CSV, and we got Polars read CSV. Sorry, I haven't actually recorded anything. Read CSV, and we'll have a look at the output. Firstly, in terms of actually the syntax here, we have try parse dates equals true. There's a date column over here, and we're asking Polars to try and parse it. And I just note that the kind of semantic thing, it's not parse dates equals true. There's a lot of thought going into the fact that it says try parse dates equals true, because this isn't a guaranteed operation. And this gives you a sense of the kind of discussions the Polars developers have to kind of indicate semantically what the operation is actually going to give you out at the end. If we have a look at what you get when you print a data frame, Polars always gives you a bit of metadata. So for example, we always get the shape up here, and below each column name, we get a shorthand version of the D type, which is just kind of handy when you're inspecting the data. The other point to note versus the Pandas ecosystem is that there's no index. So Polars doesn't have an index here, doesn't have kind of any kind of column indexes. And I'll tell you, once you kind of move away from Pandas, you don't miss the index, because you realize how much of your work is actually just managing indexes. Whereas Polars is really fast without actually needing for you to spend all this time setting and resetting indices. In fact, this week in my own work, I was doing some Pandas code, and I came across a column multi-index for the first time in a while. And yeah, I was glad I hadn't had to deal with that. Kind of bit of essentially a nice idea, but a bit too complicated for actual day-to-day use. If you notice, the default setting is for Polars to print out quite a lot of rows here, maybe like 20. And one nice feature is that it's quite easy to configure this kind of thing, because within Polars, we have the config namespace, and we have a bunch of functions here for actually adjusting things like this. So in this case here, we can set the default number of table rows to be 6. And I find that I use this kind of thing all the time for changing number of rows, number of columns, how long strings are printed, how long floats are printed. And it's just quite handy. It makes it a better experience. In this, if you're interested, you can again kind of like tab complete into here to see some of the other kind of config operations. So we print the data frame again, and now we've got 6 rows. So we'll first take a quick overview of the data frame. So like in Pandas, we have a describe method, and that gives us out for each column some statistics. So count, null count, mean, stats, and then into percentiles. You can specify more percentiles here. But what I really want to talk about here is this null count. So it's 0 for most columns and 6 for radiation, 5 for temperature. Oh, I haven't talked about the data set, by the way. Maybe I'll just introduce it here. So this is a time series of dates, so day by day data from 2015 to 2020. Load is kind of the UK electricity demand in gigawatts. So megawatts. So this is like 48 gigawatts and down to 31 gigawatts. And then these are a bunch of features which we're going to try to use to kind of forecast what the load will be. So that's the kind of data set that we're looking at, and we'll fit a machine learning model to below. So we're talking here about the null count, and we see here in global radiation, there's 6 rows with null values out of about 2,000. And one important thing to know is that Polars always counts the number of rows that are null. So if you ever kind of need to know that, it doesn't actually have to search through the entire data set to find the nulls. This is one of the things that Apache Arrow does. It has a consistent representation for null values across all columns, and missing value is just a null. And it also stores that as a bit of metadata, so that, for example, you can do, if you have a column which actually has no null values, or sorry, no actual valid values, it's all nulls, the Polars can check for things like that before doing extensive calculations. And so just kind of keeps track of that. And it's kind of part of the more sensible way that Polars handles missing values. There's an alternative way. If you've got a very wide data frame and you want to get a look at what's going on, we can print df.glimpse. And it's kind of like a head operation, but done vertically, so that on each row we have a column and we can see the first few values on each column. So there's also quite a handy way for working with wide data sets. So that's a bit of an overview of how the data frame works. Now we're going to touch on how the Polars API works. And so we'll do that here by looking at how we select and transform data. Now there is one way of doing it using square brackets. So for example, here we have a data frame, and we're going to select the first 3 rows and the time and load columns. And this is fine as far as it goes. And this is kind of what people are familiar with if they're familiar with Pandas. However, this isn't the primary way that we kind of select and transform data in Polars. What we do use this for is when we just want to kind of get some data out, say to inspect it quickly, and we're really thinking about a one-off operation. So you might be working here in a notebook and you want to look at some figures, we use the square brackets. However, if we use the alternative approach, using what's called the expression API that we meet below, we'd see we get a lot more benefits. And so that's what we're going to focus on. So the expression API, so here's an example of it. There's 3 kind of key methods that we use with the expression API for selecting and transforming data. It's filter for kind of selecting rows, select for selecting columns, and with columns that we'll see below. So here we're going to select some rows. So the data frame, we call the filter operation, and here's how we express this. This is our kind of expression API happening here. So we use this pl.call function, and in this case, we give it the column name time. And here's the condition we're expressing on it, that we want this time column, all the rows satisfy this condition of being before 2020. If we look down to here, we see the last row is the end of 2019. So this is kind of the key bit that is kind of you need to learn as you're learning Polars, is just that you work with this expression API, and we'll see why below. If we want to select a subset of columns, so here with filter, we select a subset of rows. To select a subset of columns, we use a select method. And in this case, we're going to give it 2 columns, the time column and the load column. And we do that. And, well, I'll talk about this in a second below. But if we want to add or transform a column, we use the with columns method. So here we're going to do a little bit of feature engineering, and we're going to add 2 columns. One from the date column or from the time column takes the day of the week, and another column which has 1 day lagged values for our forecasting model. We're going to call this df2. So we have original data frame. We call with columns. So whatever happens in here will just add or transform existing columns. And so because we're specifying a new column name, day of the week, we're going to add a column here. And the way we do that is like this. So we call the pl.time column. We tell pullers, take the time column, and dt is a special namespace for temporal operations. And in that, call the weekday function, or the weekday expression. So that will take those dates and pick out what day of the week it is. And for our lag, we're going to call the load column, and we're going to shift it back in time by 1. If we run that, we see we have our original data frame, plus a couple of new columns over here, because we're using with columns. Now, one of the key points to understand is that when we give pullers multiple columns inside here, it runs these operations in parallel. So here we have these 2 operations. The pullers went off and ran them at the same time. And this is obviously one of the major sources of kind of speed up compared to something like Pandas. And also you can just see how kind of easy this is for you. And we'll see below that, although here it might seem a bit verbose, they're having to kind of write this out, that what happens if, say, we have dozens or hundreds of columns. We'll see below that actually it's pretty easy to specify these expressions for lots of columns at once. And then you can imagine that you're getting lots of parallelization happening underneath the hood. As regards visualization, I'm going to visualize these features using Altair. So this is just standard Altair code. So in this case, we're going to take our df2, which is our data frame with the features, and we're going to look at the load and how it varies by day of the week. I'm going to do it as a box plot, and the x-axis will be day of the week, y will be load, and the color will also be the day of the week. So here's our plot here. So x-axis day of the week, y-axis the load, and we can see that we've got lower load on lower demand on weekends compared to weekdays. Now, I just want to kind of reflect on what's happening here. So Altair is a third-party library, and up until the most recent version, it didn't have support for polars. It just was based on pandas. But with this recent version, it is actually supporting polars data frames without needing to convert them to pandas. And it's doing that using something called the data frame interchange protocol. So this is a new idea that's being implemented by lots of different data frame libraries. And the idea is that they've all got kind of background code that third-party libraries can access to do the same operations. So in this case, to select, for example, 2 columns, that although this library doesn't kind of actually work with polars directly, that inside polars, there's code that it can reach into and say, okay, here's generic code that should work in any data frame library. And so it can support that. Similarly here, we write do another Altair chart, and this is looking at the lag feature. So in the x-axis, we have the lag values from the day before, and the y-axis is the target values. And we can see in this case, we've got the strong linear relationship, but shifted up and down for the different days of the week based on their mean demand. Now, I've written more on visualization with Matplot, Plotlib, Seaborn, and Plotly in these blog posts here on my website, which I encourage you to look at. But just one of the interesting points is that none of these libraries have explicit support for polars, but in general, you can actually pass the polars data frame directly to them. And that's because that when they're inside their API, they're not actually looking for a data frame. They're just looking for an array that they can iterate through. And so with polars, it has the code in there that with Matplot.lib, which has never heard of polars, is given a data frame in the right way, it can still render your plots. So you're not hindered in terms of your visualization options working with polars. Now, one complaint that people have is that they find the expression API a bit verbose, all this pl.call and writing column names everywhere. But one of the kind of handy areas I find is that there are lots of ways of actually working with lots of columns all at once. So there are a few ways of going about this that I'll introduce. And I think it's important to kind of learn about these early, because if you are sitting there just typing out column name after column name, that I don't think you'll really have a happy experience. But one thing that I use a lot, for example, is here's an operation where we take our data frame with the features, and we're going to transform some existing columns. And in this case, we have our pl.call operation to specify what columns we want. But in this case, instead of passing the names of all the float columns, we can just pass this pl.float dtypes. And so polars will just understand that we want to do the same operation, which is rounding off the values to 0 decimal places on all of the floating point columns. And there are similar things here for floats, integers, date times, and so on. So often this is really handy if you're doing a group by, for example. You might group by a date column, and then you want to, say, take the average of all the floating point columns. you don't need to write out all those column names. Instead, you can just pass the dtype. A new innovation in this area is the Polar selectors. So this is a kind of namespace within Polars that has a bunch of methods for making it handy to access lots of columns at once. So in this case, we have our data frame df. We're going to select, that is, get a subset of columns. We want the time column first, and then we want all the columns that have temperature data. So in this case, we use the cs.contains, and we pass it a string. And so this looks through and finds all the columns that have underscore temp in the column name. So this is quite efficient, and there are a bunch of other functions in here. I've put a link down here to the official docs, which are a really well-written page. And you can see there's things here like for matching dtypes, or for passing in regex, or for looking for sort of columns that start with a certain letter or end in a certain way, and a bit like the built-in Python string types. So this is also makes it really handy to work with lots of columns. So why should we use expressions instead of the square bracket approach above? Firstly, expressions, as I said, can be run in parallel. So when you get multiple expressions, and so here's another example where if we were doing transformations on this, all of these will be run in parallel. The expressions will do that automatically. Secondly, when we do expressions as part of a lazy query that we'll see below, the expressions can be optimized. So Polars can look at the full set of operations you're interested in and try to optimize how they run. And also with the square bracket indexing, that only works in eager mode. But when you use expressions, you can use that in lazy mode as well. So it's a bit more flexible. So the idea is to kind of use the square bracket indexing when you're trying to just pull a kind of single value out of the data frame. Otherwise, just work with the expressions. I'm going to touch on fast track algorithms and sorted data. So Polars is fast track algorithms if it knows a column is sorted. And so if the algorithms that it has fast track operations for are things like statistics. So take a max operation, for example. If you're looking for the maximum in a sorted column, it's just the last non-null value. Similarly, with say a median, if you're looking for the median in a sorted column, then it's basically the 50th. We look halfway through the array, and perhaps you take two values and interpolate or something. But essentially, doing a median operation requires a sort. But if Polars knows that column is sorted, it can just jump to the right place in the array to get the data. We also fast track operations on the sorted column for a filter. So if you're say filtering for all the values below a certain point, Polars knows when it gets to the first value that's above it that I can just stop searching through the rest of the array. And there's also fast track operations on group bys and joins. That's in terms of the group by key and the join key. The way we do this, so to do this, Polars has to know that a column is sorted, so it doesn't actually check it itself. This is some metadata that we give it. And we can see how we do it here. So we have our data frame. We're going to transform a column. And in this case, we're going to tell it that the time column here is, by calling set sorted, now we tell it that the time column is sorted. So if you call that, there's no actual difference in the data frame because this is really metadata that's changed. But we can see if we look at the flags attribute on a column, that we have this thing here now, sorted ascending true. So now if we were to do some of these operations, that on the sorted column, that we find that to be faster. Now I've written some blog posts on this that kind of go into more detail. This first one here kind of introduces sorted algorithms and this set sorted thing. And then if you're interested, check out this one on group by with sorted algorithms. And it explains how this kind of effect of the sorted operation really depends on the cardinality. So if you get a sorted column with only a few entries, then you'll get a much bigger speed up compared to a sorted column, which has kind of very few unique or lots of unique values. So actually, Polar still, in that case, still has to basically go through the entire thing. Lazy mode and query optimization. So far, we've been running what we call in Polar's eager mode. And in eager mode, every line of code that you do kind of runs at once and outputs a data frame. Instead, in Polars, we also have what's called lazy mode. And in lazy mode, instead of actually kind of running the code each time, what we do is each operation adds to a query plan that builds up and it gets optimized and then is finally evaluated. So it's pretty simple to move into lazy mode. If we're starting from a data set on disk, we can replace read underscore with scan underscore. So here we have scan CSV instead of read CSV, and you'll see that the rest of the syntax here is the same. If we run that and we print out the output, what Polars prints here is the output of that, what it's called the naive plan. And the naive plan is basically the operations, the query plan in the order that you've given them without the query optimizer having been applied to it. We'll talk more about query plans just below and how to read them. So it's worth understanding what actually happens here when we run scan CSV. Well, Polars doesn't actually read the full CSV file in this case, but it does actually open the CSV file, looks at the header names, and looks at the first n rows, where you can specify that here to figure out what the D types are of the different columns. And the point about lazy mode is that Polars always needs to know at any stage of the query plan what the columns are and what their D types are. So obviously you can change those as you go through the query, but from the get-go, it has to actually understand what you're transforming in the query. But this is very quick because it's not actually reading a big CSV file. It's just looking at the first kind of 100 rows or 1,000 rows or whatever the default value is to infer the D types. Now we'll build a query where we're going to construct a df-train, the training data set, where we do our feature engineering. So I'll show you what this looks like, and this is to explain what happens in terms of the query optimizer. So you start it just as above by scanning the CSV file with the features. We do our feature engineering by adding our day of the week column and our lag column. And this is the training data set, so we're going to filter values before 2020. And we're going to say this is actually a redundant feature, so we're going to remove it. The way we do that is doing the select method to get a subset of columns, but in this case, we use pl.exclude to get rid of a column. If we just run that, we see df-train and it prints out the naive query plan below. If we want to see what the optimized plan is, and this is the plan that Polars will actually run unless you tell it not to, we use the explain method. And here's a kind of optimized query plan. You read these from bottom to top. So here it starts off down here with a CSV scan and name the CSV file. And notice here it says project 8 out of 9 columns. That's because at the end here, we told it to exclude a column. So Polars knows now that actually it doesn't need that sunshine column. What that means is that when Polars reads through the CSV file, and as it goes through line by line, that it'll figure out which part of the line is the sunshine column, and then won't actually read that into the data frame. So especially if you're selecting a subset of columns, that this can really be very memory efficient. And it's also a bit simpler than something like Pandas, where you can do something similar, but you have to specify this explicitly. And I found that I generally forgot to do it, whereas when you're using this in Polars, it just does it automatically for you. The next stage of the query plan is the transformations to add in the day of the week column and the lag column. And then it applies the filter to get the values before 2020. And then this fast project is just picking out the columns. So getting rid of the sunshine column. Now, one kind of interesting point here, and it's worth kind of understanding how optimizations work, is that what you'd really like is for this filter operation to be moved as early as possible, perhaps even when you're reading the CSV file, and not to happen after doing this transformation. But the reason that optimization hasn't happened is because we have this shift operation. And so Polars has been careful here. It's got a shift operation, which it knows affects multiple rows at once. And so it's not moving this filter up into the read CSV to reduce the amount of data we have to read. Instead, it's leaving it down here. I'm just going to comment out this shift just to see what happens in terms of the optimized plan below. And now we see the optimized plan has changed with the CSV scan, and now we have the filter next, and then the transformations. So imagine if you got a big filter here, where you're throwing away a lot of the data, that it's best to have this as early as possible. But sometimes Polars will be cautious in terms of in its optimizations, in terms of when you've got things like shift or things that might affect multiple rows, in terms of how it'll move filter operations around. And of course, it's easy to say, okay, well, you know that it's only affecting one row, so why not just make sure the filter doesn't just get rid of the row that we need when we do the shift operation? But these query plans can get very complicated, and so it's hard to be kind of aggressive about this and say, right, we're going to apply this optimization, because it can lead to kind of big problems down the line. So what kind of optimizations can be applied? So one that we've seen above is called projection push span. That's where Polars identifies that only a subset of columns from the data set are relevant. Another is called predicate pushdown. So this is the idea where we've been talking about, where it moves the filter as early as possible in the data flow. Another is combining predicates. So in Pandas, if you've got multiple conditions, you have to write them as a single condition separated by ands. In Polars, you can write those as multiple filter methods, and it'll just kind of bring all those together so that they're applied on a single pass through the data. And there's various other ones here, such as slice and the common subplan. Another one that happens more underneath the hood is the caching aggregation. So if you're doing a kind of a group by in the same column multiple times, it'll try to kind of cache that group by so that I can reuse it. But overall, with optimizations, that generally most optimizations aren't magic. They're often things that you could implement yourself. But the idea of having them in a query optimizer is that A, they're done even if you don't know they exist. B, they're done even if you forget. And C, they're done correctly if you kind of get them wrong. So the whole idea of the optimization is really not that it does something you couldn't do yourself, but that it does it just automatically and in an optimized way behind the scene. So dftrain at this point is a lazy frame, and we're going to evaluate it by calling the collect method, and that runs through the full data set and then evaluates the full query. There's also a fetch method here, which runs to only run on a subset of rows. So if you run this, we get 3 rows back. And the idea is that this is great for development and debugging, that if you've got a big query, which takes a while, you can run the fetch query so that you only have to run it for a few rows. This can be handy because if you get a more complicated query plan where you're joining multiple data sets, for example, that you might get issues like different D types on the different columns and different data frames, and that can be slow to run the whole thing. And so you can run fetch to just kind of run a limited amount. It works a bit like a limit in a SQL query. Finally, in this section, I'm going to talk about streaming large data sets. So Polars can process the lazy query for larger memory and data sets in batches. So in the default mode, without streaming, what Polars does is read the entire data set into memory at once. Whereas in streaming mode, it'll read chunks of, say, 10,000 rows at once and try to process them in a full query and then bring them together at the end. If you want to run in streaming mode, then you pass the streaming equals true argument. And that's essentially it in terms of what you have to do do this batch operation. So there's some resources here. So I've made this YouTube video, which kind of gives a high-level introduction to streaming. And I've written kind of more detailed blog posts, such as this one, which talks about how you set the parameters, such as the number of rows and so on. And I cover it more in the course. The thing to know with streaming mode is that, so for many core operations, for streaming mode is that it has to be kind of implemented. It just doesn't come for free when you do this. The developers actually have to go and make sure that a given query can be run in batches. And the way, if you're curious that sometimes you run a query in streaming mode and you find that you're running out of memory and you think, well, why am I running out of memory? I should be running this query in small batches instead of all at once. And the way to check what's happening is again the explain mode. And this time you pass the streaming equals true argument. The key point here is that when you run with the streaming equals true, that there should be a part of the query plan. With this, that starts with this pipeline and ends with end pipeline. And basically any part of the query plan between these will run in streaming mode. So we see here that actually the transformations we have in the with columns and a filter aren't running in streaming mode. So what Polars will do in this case, when it evaluates the query, is it'll just read from the CSV file in streaming mode in batches. It'll then materialize all of that as one big data frame, and then it'll start doing these other transformations. The reason for that, so the reason it's not doing the entire thing in streaming mode is again the shift operation. So if you think how a shift operation works, is that you're pulling data in from the next row down. However, if you imagine that you're working in batches and you've got the first 1,000 rows in one batch and the next 1,000 rows in another batch, that you don't have inter-batch communication, so that one batch can't know what data it needs to pull in from the next one. So by having the shift operation here, it's broken the ability to do streaming mode on the full pipeline. So in this case, if you're struggling with memory, it might be worth, for example, moving the shift operation to later, so after you do the filter and your data size is reduced. But and actually, I'll show you actually what happens if we remove the shift operation. So we create dftrain again as a lazy query, but without the shift operation, and we explain what happens in streaming mode. So we see in this case, without the shift operation, the pipeline part runs from here to here. So this entire operation will now run in streaming mode. And so it's worth considering if you're having memory issues, if you can identify queries that aren't working in streaming mode. And so things like the shift operation, things that require data to go between batches, they're the kind of things that will break streaming mode. However, the good news is that lots of really the core operations, such as a kind of filter operations, group bys, joins, they're all supported in streaming mode. So you should be able to do kind of like the bulk of your work in that way. So I'm just going to check. So there's some questions in the chat, and I'll come back to those at the end. Oh yeah, sorry, this is just the example above I did where I commented out the streaming mode. Okay, we're in good time actually. So we're going to come on to the last little section on machine learning. So this is a really fast-moving area of the kind of the ecosystem. So on today, which is the 27th of July, 2023, you convert to NumPy when you want to pass data to machine learning libraries. There is one exception really, which is XGBoost, which would accept Arrow, but support for that is a bit kind of unsure at the moment. So I actually convert to NumPy for XGBoost still. So you convert to NumPy or NumPy back to Pandas when you're passing into machine learning libraries. One thing about that is that in the context of my machine learning pipelines, this conversion, having to copy the data to NumPy, is generally a really small part of the overall runtime, like maybe 1%. So I see some people really get like hung up on the fact that you have to do this copy, but Polars is so fast in terms of how it reads data and processes them, and even how fast and how it converts to NumPy, that this really isn't worth worrying about if this is a kind of in your pipeline. However, the whole situation is changing very fast. This is a scikit-learn issue thread, which is being active this week, where the developers and some other prominent people in the ecosystem are talking about how scikit-learn can support Apache Arrow-based things and Polars in particular. So there's going to be a lot of change in this in the coming months, I expect. Okay, so we're going to define a simple machine learning pipeline. We're going to use CapBoost, which, if you're not familiar, is a gradient boosting library, a bit like XGBoost. I really like it, and I've used it multiple times in production. I find that compared to XGBoost, it's a bit more stable, gives slightly better performance, and yeah, it's just definitely my go-to for tabbing your data. Down here, we have this check here to see if dftrain is still a lazy frame, and if it is, to collect and turn it into a data frame. This is the kind of thing that you end up having in these notebooks because you can't call collect on a data frame. That'll give you an exception. So, and because dftrain at some point in your notebook is a lazy frame and some point is a data frame, that often you have this kind of check-in just to make sure. Then we're going to fit a model. So it's a regression model to predict the electricity demand. So we're going to take our dftrain, we're going to drop the time column and the load column. So we keep all the feature columns, convert that to pandas. And here we pull out this single column here as a feature. This is our target vector here, y, and we'll fit the model. That'll take a minute. And we're going to, while that's running, we're going to define this to get our test data frame. And so that's similar to what we had above, except that we're going to look for the records after 2020. And we're going to create our X test, which is taking this data frame and converting it to pandas with just the features. Now we're going to create a data frame that has our out of sample values and along with their predictions. We're going to call that prediction df. So that's our df tests. And I'm going to add a column here, and we're going to add a column from the model. So the predictions are going to be like a NumPy array that comes out of CapBoost like this, a one-dimensional NumPy array. We turn that into a series, give it a column name, so like a one-dimensional polars object. Run that, and we see that over here at the end, we now have our prediction column. Going to visualize the outputs, and again, we use alter. And just kind of highlight one of the little points that happens here. We have our prediction df. We just want to have the time, load, and prediction columns to test our predictions. We're going to melt because alter wants things in long format rather than wide format. And this is the kind of little issue that can happen when you're interacting through the data frame interchange protocol, is that alter doesn't like the polars date format for some reason. So actually, I cast the date format into a date time, and it thinks that's just fine. I give the plotted title a width, and then I just use standard alter stuff to plot it. And this is what it looks like. So we're going here over 2020. The blue is the actual values. and then the orange is our predictions. You can see it works pretty well through here until lockdown hits, and then there's kind of a big divergence over the summer, and then it keeps on kind of just diverging like that. So obviously this isn't a machine learning masterclass, but yeah, that's how you can do your machine learning pipelines with polars relatively simply. Okay, I'm going to come to the end of the demonstration part and start kind of opening up the questions. But say the next steps are the most important one is to try polars on your own data. This is how I got involved in the project about 15 months ago. I had a project where I had a quite large CSV file that I would open, and it would take about 45 seconds to open. So normally I would run pandas read CSV, and then I would start flicking over to Twitter or something like that. And then I tried it with polars, and I was starting to flick to Twitter, and I realized the data was already loaded in like a second. And so it was like, okay, wow, this is a major improvement. Check out the course materials if you've got them, or if you want to sign up for the Udemy course. I think this is obviously I'm biased, but I think it's the best way to really get up and running with the library really quickly. If you get stuck, post questions on Stack Overflow. There's a really active kind of group of users there who like to answer polars questions. And if you want to discuss where the library is going or other ideas, join the polars Discord. There's a really active forum for users and developers to kind of interact there. Yeah, so that's kind of my kind of intro to polars, and so I'm looking forward to hearing what you think and what your questions are. Kwan, are you on mute?
Okay, sorry. Thanks very much, Liam, for very informative talk on the polar library. So now we'll stop the recording and take question.